So if I break it up into 3 pieces, then I can go ahead and find the X values there because we chose nice numbers. So if I break that up into 3 pieces, my X values here are going to be 1 and 2. If we're using the right-hand side of each region, then for my first interval, that means I would use the 1, plug it into the function, and draw my height there. For the second interval, I would use the 2, plug that into the function, draw my height there. And then I would plug the 3 into the function. What do we get when we plug 3 into the function? So that height is 0. So it kind of only looks like 2 rectangles in the end. Technically, we've still got 3. So if I call these area 1, area 2, and well, that's area 3, but each of these has the same width. They all have a width of 1. So we could factor the 1 out of the whole thing. And then because we're using right-hand endpoints, we would end up looking at the height at 1, the height at 2, and the height at 3. F of 1 is 2, F of 2 is 1, and F of 3 is 0. By the way, will that underestimate or overestimate the area? Right. I know that for 2 reasons. I know that just looking at the graph, each of these rectangles is below the graph. I also could tell that because we know what the area is. We already found it. It's 9/2. And we just came up with a value of 3, which is definitely less than 9/2. Now for the fun part. So I mentioned that mathematicians often are looking for ways to minimize their effort on the problem, but maximize accuracy. So mathematician walks up to this and says, hey, it wasn't very accurate with only 3 rectangles. I can get more accuracy if I use more rectangles. So instead of using 3 rectangles, what if I decided to use 6 rectangles? I'm not really going to do this. Please don't draw this. But if I used 6 rectangles in here, stick your hand up when you know how wide each rectangle is. You won't have to talk, I promise. Keep your hand up if you're willing to talk. Really, so many hands melt. I know. Hi, I'm Sara. You are? Yeah. Okay. What are you thinking the width of our rectangles are if we've got 6 of them? How many people were thinking the same thing? 0.5, 1/2, whichever way you like it. Okay, cool. I actually don't want 6 rectangles in there. I want to shove 20 rectangles in there. Stick your hand up when you know how wide each rectangle is. Keep it up if you were thinking 3/20. Cool. I'm actually not interested in even 20 rectangles. I'm going to shove a bajillion rectangles in there. Now, how many is that really? I don't know. I'm just going to call it n for some big number. How wide is each rectangle? Totally. So the width of each of my rectangles now is 3/n. Now, this picture isn't going to help me because I can't really draw a bajillion rectangles in there. So if you want to draw something on your paper, here's what I recommend drawing. It's going to be my fake picture because I'm just going to use a ... So, got this thing here. I'm going to choose to use right-hand endpoints. And there's a reason for that. And we'll talk about the reason for that. But I'm going to choose to use right-hand endpoints. And I'm just going to draw in a couple of rectangles. And then I'm going to go ... and draw in another rectangle here. So this is my first area, my second area, my third area, and I'm going to use the letter in the textbook, and I actually don't remember, but maybe one of you will tell me. I or K? Is this meaningful to anyone? Not yet? Cool. K. I didn't watch the 12 o'clock lecture, so I didn't know if it came up there. I only watched the 9 o'clock lecture. Okay. So I'm going to start finding the areas of these rectangles, keeping in mind that each one has a width of 3/n. Now, if I want to find the area of a rectangle, I need a base and a height. I figured out what all my bases are. My bases are 3/n. And to figure out the height, I kind of need to know the x values I'm plugging in. So if we started at 0, and the width of this rectangle is 3/n, then what's the x value right there? Cool. And by the time I get to the next one, I've moved 2 of those. So I'm not at 3/n anymore. I'm at 2 of the 3/n. Yeah, you could call that 6/n. That's totally fine also. By the time I get over here, I've moved 3 of the 3/n's. And by the time I get to my kth rectangle, I have moved k of the 3/n's. I'm looking at my paper and trying to figure out how I'm going to squeeze this in, but I think we can do it. So if I start writing the area, they each have a width of 3/n. So if you're comfortable with that, I'm going to go ahead and factor that part out. So I'm going to factor the 3/n out because that part was the base. And then when I start to do the heights, that first height that I plug in, if I'm doing the right-hand endpoints, then that first height that I plug in is the 3/n. So I got my function, I'm going to plug 3/n into it. And then the next one, I've got my function, and I'm going to plug 2 times 3/n into it. And then my next one, I've got my function, and I'm going to plug 3 times 3/n into it. And I'm going to keep doing that. Somewhere along the way, I'm going to have that kth rectangle, and I'm going to have k times 3/n into it. And I'm going to keep going. And by the time I get to my last rectangle, if I'm using right-hand endpoints, what value should I be plugging in? I'm going to get 0 for the height. What's the x value I'm plugging in? Right. And I could write that 3, or I could write that as n times 3/n. Not that you had to like this section last quarter, but how many people remember when we were doing sequences and you had to like find the rule for the sequence and write what the rule for the sequence was? I see some head nods. Yeah. So now I'm going to do exactly that. I'm going to look at this and say, well, what's the rule? This rule is pretty simple. This rule says, I just take which rectangle I'm on and I multiply that by 3/n. That's the rule. So we can take this entire expression, and this is where I'm about to lose people because I'm going to flip the page. So this is not going to be sitting here anymore. Sorry. I ran out of space. I don't want to lose you. You'll be okay. Recap. My area looked like 3 over n times this whole thing, and we had f of some stuff. Yeah. This whole thing, mathematicians, minimize effort, maximize accuracy. I'm going to minimize effort. It sure would be nice to have a shortcut way of writing all of that. And our shortcut way of writing all of that looks like I've got that area, I've got that base piece. In here, all of that was being added together. So we can use summation notation. And for each of those things that was being added together, what we had was f of k times 3 over n. And summation notation wise, I can say that rule started at k equals 1 on the first rectangle and ended at k equals n on the last rectangle. And if I get one step fancier on this, it's not really fancy. I'm just going to go ahead and plug in the k times 3 over n to our function. And as a reminder, our function was 3 minus x. So this whole thing over here is kind of like the x value that we're plugging in. So we would have 3 minus k times 3 over n. I said we were going to do fancy calculus stuff and get back around to the answer that we started with. Now is the part where we're going to do fancy calculus stuff. But I'm pausing here to take questions before I do anything else. Yeah. Where did you get the 3 minus from? Oh, that's from our function itself, because f of x was 3 minus x. So I'm like plugging in that for x. Yep. Excellent question. Cool. So now we have to have a little bit of an aside about summation notation. And I know that in lecture, Dr. Challenor went over like deriving one of the summation rules. You're not going to be expected to derive the summation rules. Don't worry. But you will be expected to use the summation rules. They're also in the textbook. And I don't know this for sure, but I could definitely see him giving them to you on the test, but you having to know how to use them. So pause for some summation rules. I'm going to start with, oh, by the way, the book uses K, but I is also a standard letter to go in here. Your TA would definitely be comfortable with you using either letter. And if you all want me to switch to I, I'm happy to. So I'm going to use K for now until someone tells me to switch to I. So I'm just making something up here so that we can practice reading summation notation. So what this says is the thing that I'm adding up is 2. That's my rule. You will notice there's nowhere to plug in a K. So my rule is exceptionally boring. This says when K is equal to 1, the height is 2. When K is equal to 2, the height is 2. When K is equal to 3, the height is 2, because there's nowhere to plug in the K. The summation part means that I'm putting addition between each of these. The 1 on the bottom tells me where to start, and the 10 on the top tells me when to stop. So I would keep going, adding 2 each time until I got to 10. What would all of those add up to? Yeah. What's the shortcut way to get to the 20? Yeah. So as a general rule, if I am adding up from k equals 1 to n of a constant, that result is the constant times n. How many of you have looked into your future and know that eventually you're going to take stats 100? If you haven't looked into your future, eventually most of you are taking stats 100 or PLS 120. Either way, the summation notation is going to show back up in stats. So just putting it out there on your radar that even if we don't do a ton of it this quarter, this is just kind of a brief introduction to the summation notation, and it's going to show up again in stats. And that one in particular is definitely going to show up again. Yeah.
So like 2 is that the y value?
Right. So here it's like the 2 is the y value. There wasn't anywhere to plug in the k. So it's the y value at every single point. Yeah. Or in this place, I'm just putting a constant in, that it's a constant y value. So the k value, just to make the analogy to when we were looking at in 17A, when we were finding rules for sequences, and we would use n as the letter and say like the nth term in the sequence and have the rule for the nth term. Unfortunately, we used n for the number of rectangles. So we just need a different letter to use now. So the different letter we're using to tell us which term of the sequence we're on is k. So k is just telling us which term of the sequence we're at. And the number at the bottom tells us where to start. So thinking back to 17A again, sometimes when we were writing our sequences, we would start at n equals 0, and sometimes we'd start at n equals 1. This is just telling us, like, are we starting at 0 or are we starting at 1? And then the number on top tells us how many terms to go out. Does that help a little bit? Yeah. Okay. So that would be if my function was like literally just a constant. There's another rule, and this is the one that he derived in class. So this would be equivalent to saying like my function is just y equals x. That's kind of what this one is equivalent to. This one, I'm going to start writing out the terms. So this would tell me when k equals 1, my height is 1. When k equals 2, oh, let me not go to n, let me go to 10 really quick, just like I did on the other one. When k equals 2, my height is 2. When k equals 3, my height is 3. When k equals 4, my height is 4. And I would keep going all the way to 10. Now for this particular example, adding up the numbers from 1 to 10, does anyone have a shortcut way to do it? So if we were multiplying, then we could definitely write this with a factorial, but with addition, that doesn't really work. Sometimes people are just like really good at number puzzles, and sometimes someone will be like, oh, we see a way that we could do it. This is sort of the way that it was presented in lecture, but he did it with ones and ends and didn't actually have numbers here. So what's 1 plus 10? It's not a trick question. Okay, how about 9 plus 2? And 8 plus 3? And 7 plus 4? And 6 plus 5. So if I pair these from the outside in, each pair adds up to the same thing. So each pair adds up to the same thing. So that ended up being how many sets of 11? So this worked out to be 11 times 5. You don't need to memorize that version of it. This is the version that he gave you in lecture. And that is n plus 1 times n over 2. And sometimes that's just written as n plus 1 times n all over 2. And that's really the version that we're going to use the most. And just to go back to what that looked like for us, 10 plus 1 was our 11, and 10 divided by 2 was our 5. And one of these two numbers will always be even, so it'll be okay that we're dividing by 2. Okay, now we are armed with everything we need to really, really, really do this problem. So just because I can't fit everything on the screen, I'm going to bring back up our summation. Looked like we had a 3 over n out here because that was the base of each of our rectangles. And then we had the sum from 1 to n of 3 minus k times 3 over n. Oh, there's one more important summation rule that I forgot. The sum of the sums is the sum of some sums. We don't really need to know that. It's more like a tongue twister. Kind of like when we're taking derivatives. And if I have addition or subtraction between the pieces, I can like look at each piece separately. Or if I'm plugging in values to a polynomial, I can like look at each piece of them separately and then add them up in the end. I can do the same thing here. So I have a 3 minus the k times 3 over n. Well, I can break that up and say that looks like the sum of 3 minus the sum of k times 3 over n. I'm really worried I'm going to run out of space again, but I'm going to try. I'm really, really going to try. Okay. This first one, that 3 piece, it's just a constant. So this says I'm adding 3 plus 3 plus 3 plus 3 plus 3 plus 3 n times. So all of that's going to add up to 3 times n. This piece over here, a little more complicated. The k part is the one that's attached to this. We have a formula for what it looks like to do the k from 1 to n. The 3 over n part just looks like letters. But let's backtrack for a second to what that n meant. If I have 20 rectangles, n is 20. If I have 7 rectangles, n is 7. If I had 4 rectangles, n is 4. So that 3 over n piece, we don't know what the number n is, but it's a constant. So that 3 over n would be there each time. So I'm going to write out this summation a little bit. Oh, I'm going to write out the summation, so I don't need the summation notation. Good job. Okay. So when k equals 1, I would have 1 times 3 over n. And when k equals 2, I would have 2 times 3 over n. And when k equals 3, I would have 3 times 3 over n. And I would keep going all the way to n times 3 over n. Now, in doing this, really just to illustrate a point, that one of the other things about summation is that if I have that same constant in each of those terms, I can use my favorite F word and factor that out. So if I factor out that 3 over n from this whole thing, then I'm left with the 1 plus 2 plus 3 plus 4 all the way up to n. And this part is what we know we have a rule for. That's the thing where I add the first and last term. And I know I have half as many because I've got pairs. I am just going to fit this on the page. Sweet. So this whole thing is where I'm using that formula, and we're going to have n plus 1 times n all over 2. If you are thinking to yourself right now, Sara said the mathematicians were trying to be efficient, and people think this does not feel efficient. So unfortunately, for a triangle, this is definitely not our efficient option. But for a function that isn't a nice geometric shape and we don't already know how to find the area of it, this kind of is our option for how to cram a whole bunch of rectangles in there. We're going to get to a shortcut, but not till probably next week. Well, for sure, I won't get to it till next week. You all might see it tomorrow. We'll see. Okay, I'm going to flip the page again. So I'm letting people get caught up. Not seeing a lot of writing, so I'm going to flip the page again and hope that I copied all of that correctly. So here's where we are so far. We've got that 3 over n, which was the base. And then for our height, I've got 3n minus 3 over n times n plus 1 times n all over 2. How'd I do? Does that look right? That look like what y'all have? Okay, so you shouldn't have to write it again. I was just writing it again. Okay, we're ready for the thrilling conclusion. If I want to find the actual area under that curve, how many rectangles do I have to put in there? Well, more than 3 and more than 6. Do I need more than 100? If I'm going to find the real actual area, how many do I have to put in there? Yeah. And the only way that we know how to deal with infinity is with limits, which means that my true actual area is going to come from taking the limit as n approaches infinity of this whole thing. Now, I don't know about you, but I really don't want to try to plug in infinity to that. I would like to do some algebra first. if I'm going to have to take that limit. So I'm just going to start doing some algebra. First of all, over here, look, one of my ends cancels out. That's convenient. Next up, I'm going to take that 3 over n and I'm going to distribute it in. So when I take the 3 over n and I multiply by 3n, I'm going to do it in 2 steps. It's totally fine if you do it in 1. And then I'm going to take the 3 over n and distribute it in over here. So on the numerator, I'll have 3 times another 3 times an n plus 1. And in my denominator, I'll have that n and that 2. Could go ahead and take the limit right now, but I'm going to keep doing more work. Because I would rather do the algebra for as long as I can. So I'm looking at n's that cancel out here. So that's 9. And then over here, 3 times 3 is 9. And I could go ahead and distribute that in. So I'd have 9n plus 9 all over 2n. That's probably good enough to take the limit. What's the limit as n approaches infinity of 9? Because there's nowhere to plug in the infinity. Now over here, how much work do we want to show? Let's go ahead and show some work. So right now, if I plug in infinity, I get infinity on the top and infinity on the bottom. So do you want to do algebra or L'Hopital's? Doesn't matter to me. I heard some L'Hopital's, so let's do it. So we're going to have 9 minus, and I'm just going to indicate that I'm doing L'Hopital's, and I'm going to switch this to be the limit as n approaches infinity. Derivative of 9n plus 9 is going to be a 9. And the derivative of 2n is going to be a 2. So I'm looking at 9 minus 9 halves. What did we get for the area at the beginning of all this when we just used geometry? Darn, did we get 9 halves?
Yeah.
Yeah, we did get 9 halves. Because if we get a common denominator here and multiply by 2 over 2, I've got 18 halves minus 9 halves, which is 9 halves, which means it worked. It's always good when calculus works. Yeah. We did geometry. So we had a shape that looked like this. It had a base of 3 and a height of 3. And we said, oh, that's just a triangle. That's going to be 1/2 base times height. And we got 9 halves for the area.